Welcome everyone to the week 10 tutorial session of Galois theory MA70. Today we will discuss sample questions related to week 10 lectures. So let's begin. Let pi belongs to Qx be an irreducible polynomial of odd degree greater than 1. So pi is a polynomial which is irreducible, and the degree of pi is greater than 1 and it is odd also. So we can say that degree of pi is actually greater than or equal to 3, because 2 cannot be there. Degree of pi cannot be 2 because it has to be odd. So it is at least 3, right? And of course this is odd. With only one real 0, x belongs to R. So it has a 0 and x belongs to 0, at least I can say real 0 of pi. So pi is an irreducible polynomial in Q and it has a 0 in R. So because what does this represent? This represents all the roots in I can take the notation to be alpha belongs to R, such that pi of alpha is equal to 0. So notation is as it is what we use earlier, what we have used earlier. So x is there, and this is the only root, only real root. Okay, there is just one real root in the set of zeros of pi in R. Okay, show that the field extension. So we have to show qx over q is not normal. Okay, so firstly let's recall what is the definition of normal extension. Can you tell
It
me?
is nothing but a
Yeah.
splitting field of that in the extended field must be splitting field of that.
Okay, so splitting field of what?
Splitting field of base field Q
Mm,
here base field.
uh, like splitting field, splitting field is a splitting field of some polynomial, like
Oh sorry,
yeah. So so if you say not, so you consider, let's say here this is, so I'm considering some general e
I think
over f. Yeah.
any polynomial from Q third bracket x must be split in Q open bracket x.
Okay, so you are saying you consider any polynomial, it will split.
Yes.
There is one condition that is actually, you are saying more general thing, uh, that is like Galois, simple extension Galois, that definition you are saying. So normal extension says you take, firstly it should be a algebraic extension to begin with. Okay, so this is defined for the algebraic extensions only. Okay, you take an algebraic extension e over f, and so normal extension says if a polynomial f in fx, f in fx has a root in e, then f splits into linear factors in e itself. That is f, uh, all the roots of f lies in lie in E itself. So there is a requirement, there is a hypothesis for this definition, that at least one root is there. If there is a root, then all the roots should be there. It just says this. Like for example, if you just consider, let's say, I don't know, maybe.
Yes. Then,
Hmm.
ma'am, it is true for any polynomial.
Yeah, this is for any polynomial. If a polynomial, like, you consider any polynomial in fx, and if it has a root, then all the roots will be there. If it does not have a root, there is no condition to check for normal extension. So.
But means if we take a
Hmm,
field E is equal to Q root 2, and if we take a polynomial
q root 2.
x square minus,
Yeah.
yes ma'am,
Hmm.
and polynomial x square minus 2 into x square minus 3.
Into oh, okay, so I should say, if a polynomial, if a irreducible polynomial, yeah, if a irreducible polynomial, yeah, thank you for that, this is important. So if a irreducible polynomial f, so irreducible in fx, okay, this is irreducible in f, we are not talking about in E. So yeah, thanks for this correction. So if a irreducible polynomial f in fx has a root in E, then f splits into a linear factor. So for example, what you have considered this, we cannot consider this because already this is not irreducible. So you will have to take one of the factors, right? Yeah, thanks for this correction. So yeah, we are, if you consider this polynomial, and if I define the definition to be just for polynomial, then this of course does not follow. So yeah, so you have to consider either this factor or this factor. So in both the factors, for example, if you take this factor, then root 2 is there and minus root 2 is also there. So this satisfies the property of normal extension, which says that if you consider right now I'm not saying this is a normal extension, I'm just explaining the fact. I'm not claiming that this is a normal extension, right? Yeah, yeah, this is normal also. Yeah, there is no problem in the normality here, right? Because so okay, we can check everything. So let's consider this example only. So firstly, if you consider this polynomial, then root 2 is there. So it says if you consider this to be the f, then it should split in q root 2, which is there because you can split uh, in q root 2, right? So the property is satisfied. Now if you consider x square minus 3, it does not have a root here, right? But there is no root of x square minus 3 in this extension. So so we don't need to check anything, because it says if a irreducible polynomial is has a root, then we will check that it will split or not. But if it does not have any root, then we don't have to check anything. So this is also fine. Is that okay?
Yes.
Okay, now you consider any random polynomial, so let's say fx only, which is in q root 2, right? Now we have to check that if there is a root in this, then f splits into linear factor. This is all, this is the reducible also, right? uh, Now this is something more to check. uh, I don't know exactly the answer, but firstly, one thing is there. If there is a root in, so if fx, so basically we are saying this has a linear factor. If fx has a linear factor, right? If fx has a linear factor, then linear factor in q root 2, then we can divide, right? We can divide by that factor, divide by that factor, and can get gx, okay, some gx. I've just defined gx something which is like fx by that factor, let's say x minus alpha, I don't know, some root, okay. So if we are saying that there is a root in q root 2, then there will be a linear factor. You can divide by that factor, and even more. Okay, so that I will also check. It does not have a repeated roots. So for example, let's say there are repeated roots. So you can just divide by that, and you can get some smaller degree polynomial, right? Now you have to check that whether this is irreducible or not, right? uh, so what I was saying, I don't know. So you start with the irreducible polynomial, and if it has a linear polynomial in q root 2, linear factor in q root 2, then we can divide by that and we can get something gx, okay. Now what is the requirement says you start with the irreducible factor, and if there is a root, then all the roots should be there. So gx should also split in q root 2, right? So there is one more thing I want to say. Hmm. Actually, there will, if root 2 is there, then there will be q minus root 2 also, q plus root 2 also, because this will always comes in pairs. Because q root 2, we know what is the structure. It's like if root 2 is there, because x square minus 2 is a minimal polynomial, is the minimal polynomial. Oh, wait, one more thing. Okay. I now get down to q itself. So this is a minimal polynomial in q. Minimal polynomial of q root 2, sorry, of root 2 in q root 2. So as you can see, like there is so much to check here, right? So so much to check means if you consider any random polynomial in q root, random irreducible polynomial in q root 2x, and if it has a linear factor, or what do I mean by that? If there is a root there, then all the roots should be there. So that is something you have to check in this case. Okay, actually this is a Galois extension, so it will have all the roots. That is something we also know. But okay, but by this definition you can try to check also. I don't know how to see directly here, but yeah, that can be checked. So the main point is in this. So this is actually a normal extension. Uh, right. So it says this property should be satisfied. Okay. If you assume that there's a root, then all the roots should be there. Okay. Can you say anything here? I don't know. So you start with
Uh,
fx. Yeah. Hmm.
yes, ma'am. X square minus 2 is the minimal polynomial of root 2 in cube.
Yeah, in q. That's true. Oh yeah. Right. In q itself. Yeah. Yeah. Of course, in q.
And ma'am,
Hmm.
minus root 2 is in Q root because it is a field. Minus root 2 is the additive inverse of root 2. So
Yeah. It is
it
there.
must be.
Yeah, it must be. The point is, so okay, what is the thing we need to check? You start with the irreducible polynomial. Okay, polynomial fx in q root 2x. Okay, so if if fx has a root, then you have to check that all the roots are there. That's the requirement to check whether it is a normal extension or not, right? So that is by the definition. So you assume that there is a root. So there are some things you have to do. For example, yeah, actually, like there is some work if you go like this, but there are you can think of it in a automorphism thing, and then you can get directly. So maybe we go ahead with all, all the questions. You can actually get the intuition how to do this question, because as you can see, if you start with this and if you assume there is a root, like alpha is a root of fx in q root 2. So if there is a root, then you have to say that all the roots are there, right? So that requires some checking, right? Because polynomials are of the kind, like coefficients are, so by rational root test, if it is in just qx, then you know that uh, if there is a okay, all the roots are z in z only, right? So if it is a polynomial in qx, then you know that from rational root test, and you can, okay, so, so use rational root test, and uh, you can tell something here. Okay, but now the thing is, like, all the coefficients are in q root 2. So you have to do some work to do this. So let's do these 4 questions of the assignment of non blue non star question, and then let's see if we can do this part or not. Okay, is that okay?
Okay.
Hmm.
Yes, ma'am.
Yeah. So you understand the definition now, right? We are not saying that it should split. We are saying that if it has a root, then it should split. That's the requirement for normal extension. So
Just
in
like fundamental theorem of algebra is there was a root in C.
hmm,
That after that, from there we can reduce it at most n root.
yeah. Okay, so if you go like this, it says, firstly, fundamental theorem says that there exists a root in C.
Yes, yes,
So
yes.
that is the first step, and you are saying the equivalent definitions, like if there is a root in C, then you can actually split it into n factors.
Hmm.
Yeah. So right. Okay, so you start with the irreducible polynomial, and degree of pi is greater than or equal to 3, and x is in variety of pi, like x is the only real root. Okay, then you have to prove that this is not a normal extension. So what you need to check, so you have a polynomial also, you have started with a polynomial also. So what is the thing you can check for showing that this is not normal? You have started with pi. If you can prove that the roots of pi are not in qx, because you know that x is there, right? So let's write it down. So pi is there, so pi of x is equal to 0. So there is this extension, so extension is qx over q, and pi is irreducible, that is important. Pi is irreducible in q. Okay, this is a irreducible polynomial, and pi of x is equal to 0, that is also there. So these things are there, and it is also given that degree of pi is greater than or equal to 3. Okay, and even it is odd. So it was strictly greater than 1, we have just written it down greater than or equal to 3, because it cannot be 2, because it is odd. Now so let's see. So like you have a polynomial also. Now you have to prove that this is not normal. So you start with the polynomial pi itself, because you have a root also in qx. uh, uh, Now, since x belongs to qx, okay, and pi of x is equal to 0. So to show that qx over q is not normal, it is enough to show that pi uh, does not split into linear factors in q, in qx. Okay, just understand which field we are talking about. Q pi is reducible in q. In qx we don't know. At least there is a root, so it will factor out. Like there is one linear factor will always be there because x is a root. So pi, if pi belongs to qx, so in q root 2, sorry, in qx, it will at least have a factor of this kind, and there will be some factors also, or maybe just the irreducible one, we don't know. But what we want to show that this factors, if we want, if for the normal condition, what we really require, that it should factor into linear factors, right? So there is one more thing, yeah. So for example, let's take an extension, because it is always easier where the roots lie. If we know that, then it will be easier to deal, write the roots and everything. So let e be an extension of qx, of course field extension, in which pi splits into linear factors. So basically what you are considering a splitting field of pi, containing qx, right? So that's what we are considering right now. The point is, so you have the root. So for example, pi x is equal to x minus x1, x minus x2, up to and so on, x minus xn, let's say degrees n. Okay, let me assume here itself degree of pi is equal to n, greater than or equal to 3. Okay, so right, in e, okay, so this is in ex only, like, because there it is splits, it has all, e has all the roots of this polynomial. And let's say x1 is equal to x, because one of the root is x, that we know. So firstly, can you guarantee that these roots are so one option could happen, like for example, let's say if this happens, some power, let's say n, if pi x becomes this in ex, then can you prove that this is not normal using pi? So I'm saying, for if pi x is this, then you cannot show using just pi that this is not normal, because pi splits in ex. And one more thing, pi splits in, this implies pi splits into linear factors in Lx itself. So what is L? This is in qx x. So what I want to say, if pi has repeated roots and all the roots are just x, then it will split in qx, right? Is that okay with the statement? if pi x is equal to x minus x raised to power n in ex, then pi itself splits into linear factors in qx, no? Because
Yes.
all the roots are just x. So you can write the x minus, because the coefficients will be in qx. So this will split, right?
Yes. Yes.
So this condition cannot arise, you have to prove this, right? Because I'm saying pi will be the key to prove that this is not normal. So what I mean to say, pi itself will prove that this is not normal, that suitable polynomial. Because you have to pick a polynomial, you have to say that there is a root, then you will prove that or you will disprove that all the roots are not there, right? All the roots are there. Yeah, I said this disprove also is like, uh, is that okay? So this condition cannot arise, that I am also claiming. So so what I mean to say, so there is one claim. So one more thing, uh, this has degree, n is greater than or equal to 3. So that means it is not even 2, this is at least 3. So what we are trying to say, there exist at least two factors. Because if you can prove that, okay, let me write the claim itself. Let Okay, this is a very general statement. if if E is okay, I've used E, it's E. If L is a field of characteristic 0, then any polynomial in Lx will any irreducible polynomial in Lx will not split, will not have repeated roots in the splitting field of L. Actually, this property is also known as separable. I'm not using because sir has not introduced this. But yeah, so basically this says that any field of characteristic 0 is separable. So what does this mean? That so what we are saying, you start with a polynomial, and if the field is of characteristic 0, then it cannot have repeated roots. So polynomial is irreducible. So for example, you are not considering such kind of cases. You start this as your fx in Lx, okay? We are not considering such cases because this is not irreducible. So you are taking just this if you are considering this polynomial. So you start with the irreducible polynomial, then this will not have repeated roots in the extension. And if you know, it is not true for characteristic p, because for example you can take x raised to power p minus, yeah, x raised to power p minus what should I take? Will one work? Yeah, you can take this. Hmm. Because you know that in characteristic p you can write it like this. But there is one problem. Okay, so for characteristic p, yeah, you have to take some t. T means you start with a field, let's say fp t, okay, and now you consider the polynomial here. So what we are saying, you start with a field of this kind, and t is a indeterminate. Okay, so in characteristic p, because you know that p is the characteristic, so this polynomial is irreducible because x raised to power p minus t, we have discussed that you cannot split this polynomial because if it is not irreducible, it will have some factor, then factors will involve some power of roots of t. For example, you will have something like this, or 1 by p, that is not there in fpt, right? So this polynomial is irreducible in, of course, fpt. Okay, but so we have started with the irreducible polynomial. Now let's take the extension of this. So let's consider extension here. So 1 by p, if you include 1 by p, so we can always write like this if you want. We have done such kind of questions. So you take this extension, then this will split. So x raised to power p minus t, this is actually t raised to power 1 by p raised to power p, because you know that you can take the power out, because now the element t raised to power 1 by p is there, so this belongs to fp. So this is actually same as fp t raised to power 1 by p. Okay, but now you can see this has repeated roots, like there are p roots which are equal to t raised to power 1 by p. So it cannot be so this such kind of extensions are, so extension means such kind of fpt over fp is a non-separable extension. Separable extension says if you take the polynomial, then it will split, then it will not have multiple roots. Irreducible polynomial will not have repeated roots in its extension, in the splitting field. Is that okay? So in characteristic p, this does not follow. In characteristic 0, it follows, like those are always separable. That we will prove. I'll prove here. But you understand that this is not true in characteristic p. Is that example okay? This one?
Yes, ma'am.
Okay, great. So now let's stick to characteristic 0. So what can happen? Okay, we will just go and we'll just see here. So you start with the irreducible polynomial, let clear. You start with the polynomial f in Lx, which is irreducible. Okay, now we have to prove that this extension okay, f is irreducible. Let's write it down like in this sense. So let's say this is an x raised to power n plus an minus 1 x raised to power n minus 1 up to and so on a0. Okay, where an is non-zero. We can assume that we have so n is the degree, that means degree of f is n. Of course, we are not taking degree 0 because we're not taking the 0 polynomial. Okay, you start with the irreducible polynomial. Now, so when can we say that this has repeated roots? So if it has repeated roots, then f dash x has to be 0.
Yes.
Do you agree? Yeah. So if it has repeated roots, then f dash x will be 0. Not f dash x, sorry. Repeated root. If it has a repeated root, say alpha, then f dash of alpha will be 0. Of course, f of alpha is 0, right? And if it has a repeated root, let's say that is alpha, then f dash x will be 0, because there will be a factor of square. So when you will differentiate, then one factor will still be there, so that's why it will happen, right? You can prove that easily. Now so let's see that if this will happen, then we cannot say, but so we have to contradict this property that f dash alpha will not be 0. So let's see what is f dash x. Okay, here So that will be a n x raised to power n minus 1. Okay, there's one more thing I can assume. You start with a non-constant polynomial. Okay, that is by definition itself. So irreducible polynomials are non-constant only. Yeah, from the definition from the notes itself. So this is non-constant, so that means what will happen, so you will have something like, let's say, a0 will not be there, last one will be a1, where so n is at least 1, and so x raised to power n minus 1 could be just x raised to power 0. But what could, since an is non-zero and n is non-zero, this will not be 0. Do you agree?
Yes.
Right? So this will not be 0. This implies f dash x itself as a polynomial will not be 0, because there is an involvement of x raised to power something. So this is a polynomial where at least highest degree term is non-zero. So this implies, and with degree of f dash is n minus 1. Right? But if this happens, like now if f dash of alpha, so I'm considering this alpha only, if f dash of alpha will be 0, like if it has a repeated root, if f dash alpha is equal to 0, then uh, we started with a irreducible polynomial, and we can assume that this is monic, right? If we just because we are in fields, you can just consider the highest degree term with the coefficient 1. So you start with a monic polynomial, that is also fine, right? So an is equal to 1. Okay, so that's all right. I've just assumed monic because I want to say this is minimal polynomial, just for the sake of simplicity. Right, I can say that you can still say an, but you, now I have to say that you take the an factor out and write the new polynomial gx, so I can start with itself a monic polynomial. Then what will happen if f dash alpha is equal to 0, then f dash is then f dash uh, this is itself a contradiction. If this, then this contradicts. Can you tell me what does this contradict?
Minimal polynomial.
Yeah, so what exactly with that?
Mm, it's
So there is this condition which will create a problem.
mm,
To the minimal degree of minimal polynomial, can you say
yes,
that?
yeah,
Or I want to say this contradicts to
the
the fact
factor
that,
minimality.
yeah, to the fact that fx is the minimal, because that is unique, is the minimal polynomial of alpha, right?
Mm,
Since degree of f dash is equal to n minus 1, you have a smaller degree polynomial which is 0 when you put alpha. So that is that contradicts that, because minimal polynomial are of the least degree, right?
mm,
So this is the problem. But what will happen when characteristic of p is 0? What happens, for example, in this case? In this case, when you take the f dash of x, then p x raised to power p minus 1 turns up, and that will create a problem because p is 0 in characteristic p. So the polynomial itself, f dash of x, becomes 0. Then you have the repeated roots, but that does not happen in characteristic 0 case, because n is non-zero. So that is the difference. So do you agree with this claim now?
yes.
Okay. So right, so we don't have repeated roots, so that means this implies pi of x, this implies pi of x is equal to x minus x1, and x1 I am saying x, uh, all distinct roots. But qx, now you know that x is in R, so this is in R, so there is this condition you have, and since pi x has only one root in R, this implies x2, this set, this this is in, of course not equal, this is in C and not in R, right? All are in the complex, all are the complex numbers, not the real numbers.
Yes.
Okay, so and because of that, since qx is contained in this, and now this implies all the roots are not there, this implies x2 to xn does not belong to qx, and we are done. This implies qx over x over q is not normal. Is that all right?
Yes.
Okay, great. Right. Okay. Let's see the next question then. Let pi belongs to kx, and this is again irreducible. So you start with the irreducible polynomial, and this is of degree m. Now let L over K field extension of degree m. So degree is given to be m. To show, okay, GC and GCD of n and m is given to be 1. So we have to show that pi is also irreducible in Lx. So that's a very strong condition. So for example, this is not true in general, that you agree, right? So you have started with a polynomial in kx which is irreducible, but L could be the splitting field, right? L could be the splitting field of that polynomial, then it will be reducible in Lx, right? But now it says that if the condition is the extension is of degree m, and pi is of degree n, and GCD of n and m is 1, then pi will still be reducible in Lx. Okay, so for example, yeah, so for example you start with xq minus 2, okay, and you know that if you consider q cube root of 2 and you take q, then here this is irreducible, here this is irreducible, here
Yes.
means, yeah, in qx is, it is irreducible, but when you go here then you can split it, right? So you, this will become cube root of 2, and there will be x square plus cube root of 2x plus cube root of 2 square, right? So it
Yes.
splits, it splits, and even irreducible polynomial will be just this part or this part, like this reduces. So at least this should not arise in this case. So for example, you know that what is the extension degree? What is the degree of extension here? That is 3, because minimal polynomial is 3, right? Because of the minimal polynomial degree. You know that uh, evaluation map. So from there you know the degree of mu x. So because this is a simple extension, just one value has been attached, one element has been attached. So from this you know that the degree of this extension will be the degree of the minimal polynomial in qx of cube root of 3. That is this. So degree of extension is 3 and polynomial degree is itself 3. So this is not the case, right? So because you know that that is 3, this is 3, so GCD is not 1, so it is split. So this will not happen here. And even they are not talking about uh, L is any extension. So for example, in this case, you can at least say if you start with a simple extension, you will never get such things, because simple extension has the degree. Degrees are same. Degree of the extension and the degree of the irreducible polynomial. Those are already same, right? If you consider such polynomial, you can consider some different polynomial also, right? For example, in cube root of 3, you can start with a different polynomial. So for example, I can take some weird one. So for example, you take what can you take? Right, so for example, oh, there is one more thing. Okay, I can tell you at least. So there is one more thing what I want to say. For example, you start with in this situation itself, that is your L, and you have started with Q, and that is your K, and degree of extension is 3, that we also know because of the there is because of the minimal polynomial. Now pi is any irreducible polynomial. So for example, if I might have considered this, then this will still be irreducible here, right?
Yes.
But the thing is this so here you can see degree of extension is 3, degree of the polynomial is also 3, so GCD is 3. But what we can say, that this does not this is not if and only if condition, at least we can say that, right? So as you have seen, there is one example which I am saying, if GCD is still greater than 1 and pi is still irreducible. So this does not say if and only if condition, it just says if GCD is 1, then for sure we can say pi is irreducible in LX. Is that okay?
Yes.
Okay. So yeah, so this implies the question, the conditions are not if and only if. The conditions in the question are not if and only if. Yeah. Okay. So there is this. So let's try to prove this this question. It's easy. Okay. So you have L over K and you have the degree M. Now let's see what we can do. What are all the extension we are facing here? Okay. There is one more thing. So you start with, so there is pi. Pi belongs to kx and this is irreducible. Okay. So you take so without loss of generality, or without loss of generality, let pi be a monic polynomial. Is that okay?
Hmm.
Yeah, we can do that in kx. Okay. Now what I'm assuming, let E be an extension, of course a field extension of I'll take extension of L, okay, where in which pi splits into linear factors. That is fine, right? Because of Kroneker's theorem, that there exists some field where it will split. So what you have taken, you start with E, you start with L. So there is this, was it F? No, it was K. Now let's see what is happening. We are saying that now let x be a root of pi in E. Okay, so you have considered a element which is a root of pi. Okay, now I can say that this implies degree of pi. Firstly, degree of pi is this implies pi is mu of x in k. That is the minimal polynomial of x in k. So, do you agree with this statement? So, what I have done, I have picked a root because it's good to have the root to think about the extensions. Okay, because there is a polynomial pi which is irreducible. So, without loss of generality, we have assumed that this is monic. Now, you pick a root in some extension where it will split. So, you pick a root x and you consider that x. Then you can say that pi is a minimal polynomial of x in k. Why is that? Okay, so at least you know that since, well, an explanation, since mu xk will at least divide pi, because you know that pi belongs to kx, right? So mu xk will divide pi in kx. Is that okay?
Yes, ma'am.
Okay,
Yes, ma'am.
very good. So mu xk divides pi. That means this implies pi is irreducible. Pi is reducible unless mu xk is equal to pi, right? Otherwise, what will happen? There is a factor in pi which is there, but pi is irreducible, so it cannot factor out in kx. So this is happening in kx. Mu xk is in kx, pi is in kx. It divides because we know that minimal polynomial should divide any polynomial where of which x is a root, right? So mu xk should divide pi, and this is happening in kx. So by division algorithm, you can write that expression, right? And if you write that expression, so you have that qx. So what you are saying, pi is some is the product of mu xk and some factor gx, let's say. But that is not possible because then it will be a irreducible polynomial. So both of these polynomials should be same, has to be the same, like some multiple at least. But now you know that pi is a monic polynomial and mu xk is also monic, so those has to be the same polynomials. Is that okay, this explanation? This is a standard explanation, like we are not using anything more. We're just saying if there is a irreducible polynomial, if you assume it to be monic, then that is a minimal polynomial of all of its roots actually, not even just particular one. Okay, so we have this. Now let's see what we can do. Pi is equal to mu xk. This is a minimal polynomial. So what we can do, this implies, so you have this chart. I'll still make this chart. You have L, K, lattice, and you take this kx because we don't know where x belongs. Okay, that is in E, of course, but we don't know if it is there in x or not. Actually, it should not be, but anyway. Now, and you take the extension Lx also. Okay, so what you are doing, you are taking the extensions k, l, lx, and there is this extension, and of course this is also an extension because k is contained in l, x is already x is x, we have just attached x, so that lx will be upstairs, right? You have this chart. Now you know that L over K is of degree M, right? It was given. So L over K is M, and N is given to be this. So K over Kx is N, because that is what? That is the degree of mu xk. You know that from that epsilon definition. Is that okay?
Yes.
Now this implies, now you can, so we are in finite extension, because splitting field, like we have just attached the root, so we are also in, this is also finite, so everything is a finite extension. This implies, so this is finite, so we can use the tower, degree of towers. So you have, so at one side you use this part, other side you can use this part, right, to get so what we are trying to do, so this means Lx over K, you can go from this side, so that means Lx over L, and you have Lx over L, and you have L over K, and also Lx over K, you can do it from the other side also, so Lx over Kx, and you have Kx over K. Is that okay? I've just used the tower formulas,
Okay.
right? So this implies all, both of these are of the same thing. So we can equate it. See, one side you have this, that is equal to, I can write on the same 9. So Lx over Kx, and you have Kx over K. Now, what do you know? You know that K over Kx is N, so this value is N, and you also know that L over K is M. So you have actually M into Lx over L, and you have N into Lx over Kx. Right. So what we can do, actually what we are interested in, we are saying that we have to prove that L is irreducible, pi is irreducible over X. So what we are really saying, so okay, one more thing, okay, you have pi in Kx, and so when you go in Lx, let, okay, so let pi 1, or maybe just say not even let. So in Lx, what could happen, that this reduces to something. It might happen that pi splits in Lx in some factors, we don't know, but whatever it will happen, so you take, let's say, mu x L. So minimal polynomial of x in L. X is still a root of pi. So we are interested in, let's say, of that x. Okay. So then mu xl will divide pi in Lx. Because if I'm saying, so I am interested in this extension. So I am interested in this extension now. So you know that Lx will be isomorphic as Lx over mu xl, right? Is that fine? This is L algebra isomorphism now. So what we are saying, mu xl will be there, and now you know that mu xl is there, pi is also there, because pi is in kx, so it will be in Lx also. So what we are saying, whatever will be the minimal polynomial, that has to divide pi, because pi, since pi of x is 0, so this is in the kernel, right? So because pi belongs to here. What are all the polynomials in this quotient, uh, in this kernel? That's all the polynomials which are zero when you evaluate at it at x, right? Of which x is a root. So this implies that mu xl has to divide pi. Is that fine? So what we did, we started with, so you have some pi which we know that pi of x is 0. So you consider mu xl, which is in Lx. Okay, mu xl itself, I am using the same notation that says that mu xl is the minimal polynomial of x in L. Okay, x in Lx. Then what will happen, since you know that pi of x is 0, so mu xl has to divide pi because of these conditions. Is that fine? This step, if this is fine, then I'll go ahead. I can yeah.
Yes, ma'am.
Okay.
In the one we are taking a mu x xk is the same as the pi in k.
Yeah.
Is that
Yeah. This is
now we are
this is also, as we have said, this is monic. So yeah.
okay. So we are taking a monic irreducible polynomial in LA.
In L, in Lx, right? So what we are saying that, so for example, you have just seen that if you start with, for example, x cube minus 3. So for example, in this case, we wrote an example, right? So x cube minus 2, if for example, if you start with x cube minus 2 in q, then in some extension it could split. So what could happen, that whatever factor, for example, if we are looking for the roots of cube root of 3, then you know that this will divide this polynomial. We are just saying that the minimal polynomial of the bigger field of the same x, so x is cube root of 2. So the minimal polynomial of x in bigger field will always divide minimal polynomial of the smaller field, minimal polynomial of x of the smaller field. This is always true. We have used it earlier also. So that just says that what we are saying, if k is contained in L and x is some element in the bigger field, let's say, then mu of xl will always divide mu of xk. Just that.
Yes, ma'am.
Okay, we have just used this condition. Yeah, great. So why I'm forcing on this thing, so it says if this is true, this implies, so okay, so for example, so what we are interested in, so if we want to prove that it is irreducible, so pi is still irreducible, that means what we are saying, this should not happen. Like, this should not happen means pi mu xl has to be equal to pi, because what we are saying pi is still irreducible in the bigger field. So that means it does not split. That means the minimal polynomial is still same of x in the bigger field.
But ma'am, pi is irreducible in k.
Yeah,
Kx.
it is irreducible in kx, but what we needed to show, we have to show that pi is also irreducible in Lx. That is the requirement. We have to show
Yes,
that it is still irreducible in Lx. So what does this mean? The minimal polynomial is still pi, like mu xl divides pi, then it does not split. So that means so what we are saying, okay, I'm just writing extra thing, I'll remove. So to show that mu xl is actually equal to pi, because if, for example, if mu xl is not equal to pi, this implies degree of mu xl is strictly less than degree of pi because it divides, right? Because of this condition, we know that mu of xl has to be strictly less than degree of pi. That means this is equal to n. So that means actually this here itself, or maybe let me write it like this. Since pi uh, since mu xl divides pi, this implies mu xl, this imply in so where we are talking about that, always we should write in lx. This implies pi is equal to some gx into mu xl x in lx. So what we are saying, it splits, okay, splits into linear, splits into some so we are still in monic situation. If it is not monic, there will be a constant, but constant never counts as irreducible thing, because we can always make it monic. So what we are saying, pi is equal to gx into this, and degree of g is greater than or equal to 1, and mu xl, what will happen, the degree will be strictly less than n, because degree of g is at least 1. So this will reduce, because degree of pi is n. So what we are actually saying, we are saying that pi is reducible in lx, okay. So we are saying that if we prove this, then we are done. Why? Because if it is not equal to pi, then we can write it in some factors. So that means pi is reducible in lx if this is not true, if this thing is not true. Is that okay?
Yes, yes.
Okay. So we are just saying that we have to show these are equal, but we know that now. So from this we know that then mu xl divides pi. This implies degree of mu xl is less than or equal to degree of pi. Okay. So what I'm doing, or maybe I can do. So I'm saying, actually this is a important argument, so I'm writing after this on the next page, so this is some extra. Okay, so what we have now, so there are two things. So one thing is m into lx over l is same as n into lx over kx. So there is one thing we have, and there is this other thing says mu of x l should divide pi in lx. Okay, we have two things. Now we have to conclude that these are equal. So firstly, this implies that degree of mu xl is less than or equal to mu degree of pi. And now from here, what do we have? We are interested in this actually, because you know that so this is actually m into mu degree of, you know that epsilon definition, that mu xl, degree of mu xl, this is equal to degree of mu xl. So this is equal to n into lx by kx, and this will imply n, so this n should divide. Now why I'm saying that, since GCD of n and m is 1, now we have that requirement. Since degree of n and m is 1, we must have n should divide degree of mu xl, because these two terms are same. So n has to divide either m or this part. Since there is no factor common between m and n, so n itself has to divide degree of mu xl, right? And yeah, from this side you have this. So this implies from this and this implies degree of mu xl is equal to n, because it should be divisible by n, and it is exactly less than or equal to n, so it has to be n, right?
Yes.
Okay, so yeah, so extra, or maybe, yeah, that's fine, not naming anything. So yeah, this was the requirement, and we are done. So this implies mu. This implies, yeah, that was the thing, right? This implies mu xl is exactly equal to pi, and and it is irreducible, because minimal polynomial is always irreducible in Lx. So yeah, okay, great. We go to the next question.
Yes.
Okay, great. Okay, let L is equal to k x1 up to and so on xn. This is a field extension of finite degree. This is a field extension of finite degree, of course. Not of course. Yeah, xi's are such that this is of finite degree. So at least we can say that these xi's are are algebraic. Finite extensions are always algebraic. Okay, finite implies algebraic, because you can always find a polynomial corresponding to every element because of the basis thing, you know that. Show that, to show L over K is normal. Firstly, this makes sense because the extension is algebraic. Normal definition is only defined for the algebraic extensions. If and only if L is a splitting field of mu product I is equal to 1 to n mu xk xi k over k, right? So okay, so this actually proves, if we can prove this, then we can actually prove this part also, which we have started with, right? So now you know that x1 is like root 2, k is your q here. So if you want to prove that L over K is normal, that is q root 2 over q is normal, if you can prove that L, that is q root 2, is a splitting field of mu. Now mu means mu x1k, and mu x1k here, so you are saying this is your L, this is your K, right? So you can write K x1, and mu x1k, that is actually mu root 2 and q, so that you know that what it is, that is x square minus 2, right? Because you know that over q, that is this minimal polynomial. If it splits in this, then this is a normal extension. So you can see, like, we have just boils down to proving that if this is a splitting field of the attached elements. So you understood what we are saying? Like in the beginning, what we were trying to prove, that this is a normal extension. So we started with random polynomial, and we assume that there is a root, and then there will be other roots there, right? But if we prove this equivalence, then we are done by just saying that q root 2 is a splitting field of x square minus 2. So this will be a normal extension. Is that okay?
Yes.
Okay, great. Mm, over q is normal if and only if this q root 2 is a splitting field of x square minus 2 over q, because splitting field over q. So that is true and we are done. Great. So let's try to prove the statement giving here. So proof. Let L over K be normal. So let's prove one side first. So you understood the question? So L is just some extension of like kx1 to xn. Just attached some elements x1 to xn, and this is of finite degree. So this will be algebraic. So it makes sense to say that this is a normal extension. So we have to prove that this is L over K is normal if and only if L is a splitting field of product of minimal polynomials of each xi. Okay, of all the xi's. L over K is normal. So let's see. Okay, L over K is normal. This implies, okay, can you tell me where should we start? So normality and then going to a splitting field means what? So what exactly the polynomials we have in our hands? So you have mu xi k, right? You have this. Okay, I'm interested in at least one, so we don't care. So for any xi, for each xi, okay, I is going from 1 to n. For each xi, there is this mu xi comma k. If I consider this polynomial, then can you tell me this belongs to kx, right? So can you tell me, so this implies mu xi k, not this implies, this is of course irreducible because you know that minimal polynomial of xi over k, right? So this is irreducible. Now from the normality, what do we know? From the normality, what do we know?
It contains all the roots of 4.
Why is that? Because there is one root, right? Xi is there. Since x xi belongs to L and mu xi comma k is irreducible by normality, all the roots of mu xik should be in L. So normality of L over K, right? So we are talking about L over K. So all the roots should be there, and this is true for all I. Right. Now let's try to see what is the splitting field. So splitting field says, from the splitting field condition, so we are required to prove that L is a splitting field of mu. Okay, so so let's see what, let L dash be the splitting field of mu, which is the product over over K. Okay, let's assume L dash be the splitting field. We have to prove that L is equal to L dash. So firstly, first condition, since all the roots of mu are in L, so we know that all the roots are there in L because we have proved that all the roots of mu xik is in L. So product, so this is true for all the xi, so product will split into linear factors in L, right? So all the roots of mu are in L. we have L dash is contained in L, because L dash is what? L dash is the splitting field of mu. So splitting field means this is the smallest field such that mu splits into linear factors, right? Is this direction clear?
Okay.
Yes, ma'am.
Okay, great. So what we are taking, we have X, L, we have K, and there is this L dash. Okay, great. So now let us see, because L contains K also, that's why this is true. Now since Xi belongs to L, L dash, you know that Xi belongs to L dash because these are the roots. Since Xi are the roots, are the roots are the roots of mu xi k, and hence of mu, because splitting field contains all the roots, so xi's are in L dash also. Since this is an extension of k, so over k means k is there, also k is contained in L dash. This implies the smallest field containing k and xi's will be in L dash, right?
Yes, ma'am.
So this implies that exactly is your L, because L was just k x1 to xn, and we are done, right? This implies L is equal to L dash, and one side is done. Let's try to prove the other side. Any doubts? Okay, hopefully not. So other side, let us prove the other side. Now L is the splitting field of mu over k. We have to prove that L over k is a normal extension. So sorry.
Please
Yeah.
scroll up. Sorry.
Hmm.
I really said this. Okay.
Yeah. Okay. So let's see. What do we have? Now you are required to firstly L is your splitting field of uh, mu, that is product of mu xi comma k, I is going from 1 to n over k. So this is given, or of course x is just k x1 to xn, it is given. Now we have to prove that L over k is normal. That means that what we are trying to do for root 2, q root 2, you pick any polynomial, then you have to prove that if it has one root, then it will have all the roots in L itself. So let us see. So L over k is given. Now let you consider a polynomial. There is a f in Lx which is irreducible. Better than consider f which is irreducible, and you assume there is also a root, because that is the hypothesis. If we have this, then all the roots are there, and alpha belongs to f, not f, alpha belongs to VLF. So what does this mean? This implies alpha belongs to L and f of alpha is 0. So there is one root which is in L. There is one more thing. Let me assume that this is at least of degree 2, because if it is of degree 1, then there is just one root and it splits, right? So there is nothing to check. So you start
Yes.
with at least of degree 2. Great. So and alpha is a root. Now let's see. Let okay. So you consider some extension now. Let E be an extension, be a field extension, be a field extension of L where where what splits, where F splits. So you have L, you have what was it, K, and you have E. Now E is such that F splits into linear factors. That is, E is a splitting field of splitting. L is the splitting field of L. Of F over L. So base field is now L. Okay. So and let beta be any beta belongs to E, be another root of F. Okay. So there is, you consider some other root. So what we have to prove that beta is also in L. That is the requirement, right? You consider any other root that should also be there in L. So E is some extension where F splits. So beta is there. So you pick that beta and define a map. Yeah.
Ma'am, uh, E is a splitting field of F over L. But we are already assuming that L is the splitting field of the polynomial F.
No. L is the splitting field of mu. It is not of F.
Oh, sorry.
Yeah.
Okay.
Yeah, it's fine.
F is any, we are taking any irreducible
Any irreducible polynomial. Because to prove that this is normal, what we have to check, you consider any irreducible polynomial in Lx, and if it has one root, then it will have all the roots. That is the requirement for normal extension. So we have chosen any random polynomial which is irreducible, and without loss of generality we have assumed to be greater than or equal to 2, because there is one root, and if f is of degree just 1, then nothing to prove, there is no other root, so we have nothing to prove. So at least you assume that degree of f is greater than or equal to 2. So there is some other root. Repeated roots we are still not looking, because we can also assume that there is no repeated root. Not repeated root means alpha is not that repeating root, because for example if f is something like x minus alpha raised to power n in E, then there is again nothing to prove alpha is there, right? Okay. Yeah, one more thing what I want to say.
Ma'am,
Yeah, something is missing. Alpha is there, so it cannot be irreducible also, right? Right. It is
F
not
is
of
in
L.
K.
This is, yeah. If F is in Kx, sorry, yeah. Thank you. So yeah, of course, if there is a root alpha, then it can factor it out from F. So in Lx itself, it is not irreducible. So of course. Yeah, thank you. So you start with F in Kx and you assume it to be irreducible. Yeah, definition requires F is in Kx, because normal extension means you are taking the base field also, like L over K. So it should be there somewhere. Is that okay? Any doubt?
Yes, ma'am.
But extension will be of L only, because there is some random polynomial kx. So for example, you have q cube root of 2. For example, you have q cube root of 2. You have, for example, q, and you have the extension, and you consider x cube minus 2. So it is not so q cube root of 2 is not a normal extension, you can see that, because it does not split. You have x cube minus 2, which is irreducible in kx, but it does not split properly into linear factors in q cube root of 2. It splits, but it does not split into linear factors, because you know that there is one factor, x minus cube root of 2, so that will split out. Basically what we are saying, there is a root, there is a root of this polynomial in L, but not all the roots. So this will not be a normal extension. L over k is not a normal extension. And if you say that you attach all the roots, so omega is also there, then this will be then e over k is a normal extension. So this is one example of not a normal extension. Is that okay?
Yes, ma'am.
So what we will prove, that you go to a bigger extension because somewhere roots will exist, but so roots, you can at least pick the roots. Now you will prove that all the roots are in L itself. That is the requirement. So let beta belongs to E be another root of F. Now okay, yeah, so alpha belongs to this, yeah. Now what you can do, I actually want to say that you take a automorphism. Let let phi belongs to automorphism of E over K. Okay, automorphism means from the Galois field only, so I can actually write the, okay, the Galois group. You consider phi from the Galois group E over K, the bigger one, such that phi of alpha is equal to beta. So you know that root should map to a root, and also that will only happen if you cannot write this statement if you consider phi in the Galois group of E over L. You cannot expect that, because if phi is in Galois group of E over X, then the roots of irreducible polynomial will map to roots of irreducible polynomial. It cannot happen that if it splits, then we cannot say that, right? So alpha will map to beta because in Kx, f is irreducible. Since f is in Kx, and that is irreducible, just because of this, alpha will map to beta. There will exist automorphism. Do you agree?
Yes, ma'am.
Okay, great. So f belongs to Kx, and this is a irreducible thing, such that phi of alpha is equal to beta. Now let us see what we can do now. Now you have this map, but you know that alpha belongs to, okay, yeah, that is something now. Okay, since alpha belongs to L, this implies alpha is a rational function of so function of x1 to xn, k rational function. So what I mean to say, alpha is something of kind, not f, let me write some new notations. Let's say px, p is still bad, let me write rx over qx, I don't know, some random polynomials, and x is not a good thing, x1 to xn by x1 to xn, where r x1 to xn belongs to k, like the coefficients are from k and also about q, and of course this is non-zero. Q x1 to xn is not equal to 0. Even more, since L over k is finite, implies algebraic, we also know that L of x1 to xn is same as L of x1 to xn. So denominator can also be realized as just numerator with picking, like q is invertible kind of thing, right? So we have seen that this square bracket becomes the same as small bracket. So this means, or even if you think like that, doesn't matter, we don't require such things right now, but we are saying alpha is in kx1 to xn. But this is some kind of a polynomial where where the like rational function where numerator and denominators are some polynomial in kx1 to xn, right? So just think about what will be phi of alpha, that we have to find out. So what will be phi of alpha? Since alpha is of this kind, actually I don't need to write denominator part, but doesn't matter for now. This will be same as you know that this is a phi is a k algebra automorphism. So basically k algebra homomorphism. So this is k linear and this is a field homomorphism. So that means it will since the coefficients are from k, this is over k, so k linear, so it will add up, the squares will become, so what I mean to say, this will be uh, r of what I was saying, yeah, right. So this will be phi of x1, this will be this q phi of x1 phi of xn, right? This will be this, right? Because you know that x1 square, phi of x1 square is phi of x1 whole square, because of this is a field homomorphism. And this will, in terms of addition, it will split, or respect addition, because you know that this is a linear homomorphism, k linear homomorphism. So is this a step okay? Is this a step okay?
Okay.
Okay, great, good. So you have this. Now just think about what is phi of x1 and what are phi of xi's. Phi of xi's must be the roots of mu of xi over k, because you know that this is some extension of L itself. So xi's are there firstly, and all the roots are there because L is a splitting field. Since L is a splitting field of mu, which is the product, and L is contained in E. So E has all the roots of mu xi's. So phi of xi must be some root of phi of xi comma k, because you know that root maps to the roots. Why? Because these are minimal polynomials. So these are irreducible over kx. So again, roots of mu xik will map to roots of mu xik only. So, and xi is the element. Xi is a root of mu xik. Must be the roots of mu xik. This implies this whole factor. So since you know that this implies phi of xi will belong to L for all I, right? Because you know that L is the splitting field of mu xik, so all the roots will be there, and this implies this value phi of x1 up to and so on, phi of xn, this q because these are just k so coefficients are coming from k, and these elements are coming from L, so this whole element will belong to L. And what is this? This is same as phi of alpha, and which is equal to beta, so this will belong to L, and we are done. Any doubt? So the key is you can always write the roots in terms of xi's and all the roots of xi's are there because that is a splitting field. So this is a very general statement. Splitting fields are normal extensions because that just attach one, so splitting field over some field, so this will always be like over k. So L is a splitting field over k, splitting field of, let's say, f over k, then L will be a normal extension. L will be a normal extension over k. So this is a general statement. Is this fine?
Yes.
Yeah. Hmm. So as you have seen, like, this is a very good result because you don't need to check for every polynomial. Now you have checked for every polynomial. If something is a splitting field, then it will be a splitting polynomial, and it will be a normal extension. That means every polynomial will split. Like if there is a root, then all the roots will be there. Every polynomial will split, that I cannot say. At least one root should be there. That is a requirement. Okay, very good. So let us see this question. This is very interesting. Let pi be an irreducible polynomial over k, irreducible over the field k, and you have this extension L over k. This is normal. It is given to be normal. So if it is given to be normal, that means this is a algebraic extension. Okay. Okay, so we are not talking about transcendental elements. So we have this. This is a normal extension, and pi is irreducible over k. We have to prove that if let g and h belongs to Lx. Oh, sorry. So basically, so this belongs to Lx, of course, and g and h divides pi. So what does this mean? G and h are factors of. So not just factors. Okay, irreducible also. Okay, so g and h are irreducible and factors of irreducible factors. That is fine. Factors of pi. Okay, in Lx, of course. So what we are saying, so for example, what we have considered earlier, so as the standard example we are considering, okay, so for example, if you take cube root of 2, and you take, this is not a normal extension, which we have seen, because x cube minus 2 has one root but not all, and that's enough to say, not a normal extension. So let g and h belongs to Lx are irreducible factors of pi in Lx. We have to prove that, show that. Irreducible factors, what I mean? So you have x cube minus 2 in qx, but when you go upstairs in just q, in qx, when you go upstairs, this will become x minus cube root of 2, and you have x square plus cube root of 2x, capital X, plus cube root of 2 square. Okay, so these are irreducible factors. You cannot further split this second factor. So these are irreducible factors. Now what does this say? Show that there exists sigma. So g and h are of this kind. Show that there exists sigma such that sigma of h is equal to g. So you see, like, the condition is now h is a polynomial, g is a polynomial. you're saying sigma of h is equal to g. What does this mean? So to show, okay, so we have to show that there exists some sigma such that sigma of h is equal to g. So at least, so how this happens? So for example, this is of the kind, let me take m, this, even yeah, okay, just the irreducible polynomial, so it doesn't matter. If then what will happen, and hm's are in L, okay. Right, so okay, so this will become sigma of L, and this will be just x raised to power m plus up to and so on, sigma of h0. Yeah, you know that polynomial, over polynomial, how this happens, every coefficient will map to this, right? So this is the definition. So what we have to prove, oh, sorry, I wrote,
Uh,
yeah, yeah. So this is sigma of h naught, and this is sigma of hm. Yeah, yeah, thank you. So sigma of hm. Yeah. So what you have to prove, that firstly note that, uh, okay, yeah, that is good. One thing, sigma of hm, since this is a automorphism, sigma of hm cannot be 0, because for that hm has to be 0. So we can assume, since h is a polynomial, we can assume hm is non-zero, okay. Or if it is 0, we'll start with the hm minus 1. But this means sigma of hm is non-zero, because hm is non-zero, and this is a automorphism, so 0 can map to 0 and no other element can map to 0. So sigma of hm is 0, is non-zero. That means degree will be what? Degree will be same. Degree of h and g has to be same, right? So by the map, you know that sigma of this hm, this has to be, so these are in L. So this will be sigma of hm x raised to power m, and this kind of polynomial. This implies, I'll write here maybe. This implies sigma of hm is non-zero, and degree of h is same as degree of g, if we prove this, okay. So firstly, so basically what we are saying, if we can prove first b is itself okay, show that, second says show that all irreducible factors of pi in Lx have the same degree. So question says you consider two irreducible factors, then you can find a sigma in Galois group of L over K such that h will map to g. So and you know that if h will map to g, then the degrees has to be the same. So so that means, and g and h are any arbitrary irreducible factors of pi, and you can find a sigma. So what we are saying, so second statement, b part, show that all irreducible factors of pi in Lx have same degree. This is itself true if we can prove the a part, because you can pick any two irreducible factor, and then if you can find a sigma, then the degrees has to be the same. Is that okay? And this is a very strong result, as you can see. Like we are saying, it will split into fixed degrees, like of same degrees. And of
yes,
course this is, yeah.
yes.
Hmm.
Sigma. Same degree. What is the importance you have told?
Yeah, so what I'm saying, even I can try to write. So we are saying, so firstly this was an example, so let me complete this example also. So these are irreducible factors, so a is not true. Makes sense, right? Because you have two irreducible factors of different degree. Two irreducible even b is not true. Two irreducible factors of different degree. Like you have 1 degree factor and you have 2 degree factor. So this is an counter example. Counter means if it is not normal, then this will happen. Okay, so now what we are saying, uh, enough to prove a part, because if a is true, then sigma of f will be g for any or maybe then for f and g irreducible in L x, okay, irreducible factors of pi in Lx, then sigma of, so okay, that was h, it was h, right? Yeah, sigma of h, that is, let's say, write hg, as I said, let's write hm x raised to power m plus up to and so on h0, and this is non-zero. Okay, this will be same as sigma of hm x raised to power m up to and so on sigma of h0. Okay, and this will be non-zero since sigma is an automorphism, and this implies this implies, and this map is, this is equal to g, so this implies degree of h is same as degree of g, right? Because as you can see, that is equal to m. If a is true, I am assuming a is true, so there, for every h and g you can find a sigma, then there exists sigma in automorphism of L over K such that this happens, right? So this is equal to g, and degrees are same, so B is true, B is proved. And the second part of B says, so first part says all irreducible factors of pi have the same degree. So I'm saying if we prove A, then we can prove this first part of B. And in particular, so I can actually erase this here, this might be clumsy. So in particular, if pi has a 0 in L, then pi splits into linear factors in Lx. So what we are saying, so firstly, if you know that there is a root, then all the roots should be there. And so you started with a polynomial pi, and that is irreducible. Then if you see that pi in Lx, so now it can split. So if it splits into linear factors, so what we are saying, if there is one linear factor, then all the linear factors are there. So now so that is the normal meaning of the normal extension. Now what does this say? If it factors into some degree polynomials like 2 degree, 3 degree, 4 degree, it cannot happen. It has to be the same degree irreducible polynomials. So it will be of the kind like some h1, h2, h3 up to and so on, and all have same degree. That we have to prove. That is the B part. So if we prove A part, then we are done with the B part. So essence of the question is like all the irreducible factors will have the same degree. Is that okay? So we will just prove A part and we will be done by B part. Should I go ahead?
Yes, yes.
Okay, great. So let's see this A part. So A says, so you start with two factors. So let f and g belongs to Lx are irreducible be irreducible factors of pi. So pi was irreducible. Pi was irreducible in kx, in the smaller field. Now you have extended, you are looking this pi in the bigger field where it splits. So it splits in these factors, mean reducible factors of pi in Lx, where pi is this. Okay, so now let us see what we have to prove. We have to prove that there exists some sigma such that, to show there is exists some sigma, there exists sigma which is a automorphism of L over K such that, also it is given that L over K is a normal, given that L over K is normal. This is a normal extension. That is a requirement, because if it is not normal, we have seen that there is a counter example. Like there is this counter. Right? Okay, there exists sigma such that sigma of H is same as G. Okay, let us see this. Okay, so we will try to prove like this. Yeah. Okay. You consider E, let E be an algebraic closure. You know that definition, right? Okay, I'll recall. E be an algebraic closure of L. Okay, so what we are saying, there is E, there is L, there is K. So what does this mean? Algebraic closure means it is an, firstly this is an extension of E, okay, and L is E is algebraically closed. Do you know these definitions? Algebraically closed, okay. Which means every polynomial in every polynomial in Ex. So in the bigger field itself, in E, splits into linear factors, splits into linear factors in E. So every polynomial can be can split into linear factors, and from the notes it exists. We have seen that. If you see this week notes, you can see that there exists such algebraic closure of any field. Okay, so this says that basically, what does this say? This says that roots are there, all the roots are there, like every polynomial splits. So that is one thing. Now, so this implies H and G splits into linear factors in L, in Ex, right? Because you know that E is the biggest field, like it has all the roots, just that. So H and G will split into linear factors in Ex. Okay, okay, so right, let alpha be a root of H and beta be a root of F. Beta be a root of G. So what we are doing, we are actually, we want to go from H to G. So we know that automorphisms, what we know about the automorphisms, that every irreducible polynomial have this property that root will map to any other root of that polynomial, right? We have this property, we know, from for the automorphism thing. So so what we can do, we have some polynomials, now we try to go to its roots so that we have some knowledge about what is happening on roots. Okay, Okay, so that's why I've considered alpha be a root of h and beta be a root of g. Okay, so now we have to consider some automorphisms. So let phi be a automorphism of E over base field K. So we have to be careful always that base field what we are taking as base field, because if we are interested in the splitting of sorry, if we are talking about the where the roots are mapping, so we have to always be cautious about uh, whether that is a irreducible polynomial or not, because if it is a irreducible polynomial then its roots will have that like every root will map to every other root of that uh, every other root of that irreducible polynomial. So base field defines that irreducible where it should be irreducible in kx. Okay, that's why always be careful what is the base field you are considering. Okay, so phi belongs to automorphism of E over K. Now, such that phi of alpha maps to beta. And why I am doing that again? Since pi belongs to kx is irreducible. And since f and g are and alpha and beta are roots of pi, right? Because what is happening, pi is factoring in some in some irreducible factors in lx, and two of the irreducible factors are h and g. Okay, but pi so h and g are some factors of pi, that means roots of h and g are also the roots of pi, right? So alpha and beta are also the roots of pi. So, and as I said, pi is a irreducible polynomial in kx, and phi is considered to be automorphism of E over k. So k is fixed, so that's why the roots will map to other root. Okay, because if it is not irreducible, that it is not required that alpha will map to beta. Okay, beta could be some root of some other part, and as you have considered earlier, like x square minus 3 and x square minus 2, so you cannot say that root 3 will map to root 2. Okay, until this full factor, this product is irreducible. So that is not true, because you have already written it as a reducible parts. Okay, so this is that's why I'm saying you have to be cautious about considering such automorphisms. Okay, great. So this part is okay till this part. So we have considered what we have taken, alpha and beta are some roots of pi, and especially alpha is a root of h and beta is a root of g. So you have considered a phi, which is automorphism. Even I can write Galois group. So okay, Galois group of E over K, that is automorphism group, nothing else, such that phi of alpha is equal to beta. Okay, Galois group means it is a K algebra homomorphism. Okay, you have considered such a map which exists because of this conditions existence. Great. Now there might be more, but at least there will be one. Okay, now there is a claim which I am saying phi restricted to L is L. Okay, so phi of L full field is L, because this is automorphism, so it will be. So what we are saying, when you restrict it to L, it will be L only. So I will prove that, don't worry. And this is happening because this is a normal extension. Okay, normal extension is required for to prove this part. Okay. Just go through this. I have to connect my charger. Just 1 minute.
Teacher,
Okay. Okay, so we want to prove that phi of L is equal to L. What does this mean? That is, uh, for every now I can, let's say, can I say x belongs to, x is confusing, or maybe x is fine, right? We have not used x anywhere right now. So this is a small x, some element. For every x belongs to L, phi of x is also in L. Okay, we have to prove this. Like it maps elements of L to elements of L. And this is happening because will happen for normal extensions. Okay, let us try to prove this. So let now x belongs to L, as we have taken, let x belongs to L. We have to prove that phi of x belongs to L. What does this mean? Firstly, all the elements, what do we know uh, about the mapping of this phi? As I said, we only have knowledge about the roots. So if we can write, if we can think x as a root of something, x as a root of a polynomial, then we can get some control over where x will map, because we know that x will map to some other root or even itself, only the roots of the irreducible polynomial of which x is a root, right? So that much we have control on. So let us see, let x belongs to L, then uh, and since L over K is algebraic, firstly this is algebraic, so that is important. This implies there exists some f there exists, okay, we have taken f already. No, h and g we have considered. Can I take f? We have not taken f, right? Okay, so just random polynomial f in kx such that f of x is equal to 0, and moreover you take there exists some, or even let it be, since this is algebraic, this implies uh, mu is there, mu of xn, or if you remember, this implies kernel of epsilon map x comma k is non-zero. That is the definition, actual definition of algebraic in this course at least. So kernel of this is 0, that means we can consider mu. This implies there exists mu x comma k, minimal polynomial, right? So you consider that since mu xk belongs to kx is irreducible, of course in kx, irreducible in kx. Okay, I already wrote this, so that's enough. This is irreducible in kx. This implies x belongs to and x belongs to L, and L over k is normal extension also. So what can you conclude? This implies all the roots of mu xk is in L. Can you say that? because this is a normal extension. Are you with me? So what we have started with, because we want to prove that phi of L is L, that means we have started with some element x, and since L over K is algebraic, because it is given to be normal extension, so we are assuming that this is an algebraic extension. This implies there exists some polynomial of which x is a root in kx, okay, polynomial in kx. So actually we can take that minimal polynomial itself, mu xk. Since this is a irreducible polynomial in kx and x is in L, so there is one root in L and L over k is normal, so all the roots has to be there. Is that okay? In L only, because L is normal over k.
Yes.
Okay, great. So uh, this implies all the roots are in L. This implies phi of x is equal to some root of mu xk, right? Because we are talking about irreducible polynomial, and irreducible polynomial in kx, and that is mu xk. So this implies it will map to some root of mu xk, which will belong to L. That we have proved. All the roots are in L. So phi of x will be in L. So that is a very good result, that if it is a if something is a if some extension is normal, then from the bigger field, if you restrict it to that L over K, for example, then then it will still be a automorphism. It is not true in general. If it is not a normal extension, then it will not be true. You can try that x cube minus 2 example. Okay, thus the claim is proved. And this implies, so we can actually restrict. So this implies, so phi is also automorphism, and again, as I said, I can write Galois group of L over K, phi restricted to L. I can write this is, that is, phi restricted to L is an automorphism of automorphism of L over K. Okay, automorphism, of course, K algebra automorphism of L is enough, because I said K algebra. Okay, so this is K algebra automorphism of L. This is automorphism because you know that the elements are mapping to some elements of L. So, and the bigger one is automorphism. So for every element there will be some inverse, and that will be there. Okay. So this implies, what does this mean? This implies phi of L, right? So can I say that the new name? Can I give a new name? Let's say phi dash. Okay, just some new name, nothing else. Maybe if you want, you can write 0. Yeah, or maybe I can write this phi. Okay, just this phi. So phi is such a map. This implies phi of alpha is okay. The main thing is what we were trying to prove, that we have this expression alpha and beta are some roots of be a root of f and g in E, like in the algebraic closure thing. Okay, so yeah, so phi of alpha is equal to beta, that we know. Now we have restricted it to L, and okay, now what we have to do, we have to prove that okay, what was it? Yeah, okay, now yeah, right. So you have such extensions, you don't know, so alpha and beta belongs to E. We don't know that, and of course this does not belong to L, because if the factors, if H and G are not the linear factors, then alpha beta does not belong to E. So that is one thing. But now let us see, since okay, so you consider this alpha. So first thing, you have now you have control, now you have control on phi. So basically you have got a phi, or maybe you, oh right, we can name it sigma, because we require the name, like by notation we require some sigma, right? Sorry, what was it? There is exists some sigma. Okay, so we need some sigma, and this is this, so that will work actually. So you consider this sigma, and you know that alpha maps to beta in the bigger thing, so we should not write like this. But now we have to prove that this part. Okay, why will this so basically consider, or maybe note that sigma of H and G has roots sigma of alpha, which is beta. Okay, has same roots, a common root, which is sigma of, so you know that sigma of alpha, which is equal to beta, you already know. So you know that beta is a root of G, and you know that sigma of alpha is equal to beta. That means sigma, you know that sigma of alpha is a root of sigma of H, because alpha is a root of H, so sigma of alpha will be a root of sigma of H, and beta is a root of G, and these two elements are same. And sigma of H and G are irreducible in what it is, irreducible in Lx. Okay, since H is irreducible, sigma of H has to be irreducible. This has to be true because of the map. Okay, so sigma of H and G are irreducible in Lx. Why will this be that? Because as I said, roots will map to roots, so sigma of H has to be irreducible. So both are irreducible, and uh, and mm, by and by some multiplication, and or maybe can be made monic. Okay, monic, why I am saying that monic? Because I want to talk about minimal polynomial. Since these are irreducible and these are monic, just remove the coefficient of the highest degree term. Like just take out uh, actually, yeah, it's fine. You can start with pi, we can start with pi monic. Okay, then all the factors will be you can assume that all the factors are monic. That is fine. But anyway, so these are irreducible and these are monic, so these are minimal polynomial, right? This implies of the same root, this implies sigma of H and G are minimal polynomials of beta, that is also same as sigma of alpha, right? That is the common root. So since these are minimal polynomials, and you know that that has to be unique, this has to be same, right? So sigma of H has to be equal to G. So you assume everywhere monic, that is better. Otherwise, if you assume that this is some multiple, then everything will comes with the multiplication. But that's okay. So you can assume that these are monic polynomials. And hence sigma of H is equal to G. because these are minimal polynomials, and we are done.